Welcome everyone. In this section, I will be covering section 14.5, the chain rule for multivariables. In Calculus 1 class, you have seen chain rule for single variable, one variable. Says that if f is a function of u and u in turn is a function of t, then, and if u and y and u are differentiable functions, then dy by dt equal to dy by du times du by dt. What it means is y is a function of u and then u in turn is a function of t. For example, if you write y equal to sine of, let's say, t squared plus 1, then you can write this as y equal to sine of u, where u is t squared plus 1. So ultimately, y becomes a function of t through the variable u. So when you differentiate this dy by dt, you first differentiate this with respect to u, and then you differentiate u with respect to t. So it becomes cosine u, which is outer derivative, times inner derivative, which is 2t. Then you can write u with respect to the original variable. So this expression here is the outer derivative, and this expression here is the inner derivative. So this is the idea in single variable. So here only we are extending that idea to multivariables. So state the chain rule for the case where z is a function of xy and x and y are functions of one variable. What if x and y are functions of two variables too? So we are going to see the variations to the formulas. Suppose that z equal to f of xy is a differentiable function of x and y. Then x and y are functions of single variable t. Then ultimately z becomes a function of t through the variables x and y. Z becomes a function of t through the variables x and y. So if you have to see a picturization of this, that is z is a function of two variables, x and y, so it's branching out. Then x is a function of t and y is also a function of t. Y is a function of t as well. So dz by dt, z is a differentiable function of t, and then dz by dt is defined to be partial derivative of f with respect to x, because at this point, it's a function of two variables and you are differentiating that partially with respect to x. So you have to use the partial derivative symbol, or dou f by dou x, times dx by dt. But x and y are functions of single variable t only. So you use the derivative symbol dx by dt, then plus dou f by dou y, or partial derivative of f with respect to y, times dy by dt. Then another variation, if z is a function of xy, and if it is a differentiable function of x and y, where x is a function of two variables s and t, and y is a function of two variables s and t as well, and both are differentiable functions of s and t, then the partial derivative of z with respect to x. So here you have to note, you have to look at this tree diagram. Z is a function of, you look at this diagram here. Z is a function of X and Y, so there is a tree there. Then X and Y are branching out again because they are functions of two variables, S and T. So ultimately, Z is a function of two variables, S and T, if you look at the left side of the branch. So dou Z by dou S, or partial derivative of Z with respect to S, would become partial derivative of Z. If you look at the first line, it's a partial, it is a function of X and Y. So you have to partially differentiate with respect to X, and then partially differentiate S with respect to S. Then you have to differentiate partially Z with respect to Y, and then Y should be partially differentiated with respect to S. If you notice in this diagram, we look at this part and the spot. So everything ultimately should end up with S. Then if you are differentiating partially with respect to t, dou z by dou t, similar idea. So you first differentiate z with respect to x partially, and then x with respect to t partially, then dou z by dou y, which means partial derivative of z with respect to y, and then partial derivative of y with respect to t. So here you have z with respect to x, then x with respect to t, z with respect to y, and y with respect to t. You can extend this idea for three variables even if you use a function of x, y, z, and x, y, z are in turn functions of three variables or s and t. You can extend this idea to three variables. Let's say you want to find out partial derivative of u with respect to r, then you'll have to do u with respect to x and x with respect to r plus u partial derivative of u with respect to y, then y with respect to r plus partial derivative of u with respect to of z and z with respect to r. They are only considering the left branches. So here this way, then this way, and this one. Similarly, you can do dou u by dou yes and dou u by dou t. Problem number 1 and 21 are done in the section videos. Please refer to them. Refer to section videos for these problems. For problem number 1 and 21. And what do you mean by implicit differentiation? This is kind of similar to the idea extension of the idea that you did in calculus 1 class, a single variable calculus. So if you have x square plus y square equal to say 5 of xy, so it's an implicit function of x and y, and what we do, we take derivative on the left hand side and then derivative on the right hand side, treating y as a function of x, keeping y as a function of x, then you will get 2x plus 2y. And then y, because y is a function of x, you have to consider y prime. Here, you're going to apply product rule. So it's x times y prime, x times y, where y is a function of x. So it's u v prime plus v u prime, and then you will be collecting all the y terms. y prime terms on one side and simplify. So this is how you do implicit differentiation in Calculus 1 class. The idea is the same here also, except that we are doing this for multivariables. Consider f of xy equal to 0, where y is a function of x. Let's calculus 1. Then f of x comma f of x equal to 0, because you are replacing y with f of x. When differentiated with respect to x, we arrive at dou f by dou x, which is partial derivative of uppercase f with respect to x times dx over dx plus partial derivative of uppercase f with respect to y times dy by dx equal to 0. Here dx over dx equal to 1. So if you write this differently, then it will become dou f over dou x plus dou f over dou y times dy by dx equal to 0. So if you isolate dy by dx, then it will become negative partial derivative of f with respect to x divided by partial derivative of f with respect to y. It's exactly similar to the idea that we did earlier in this problem. So dy by dx equal to partial derivative negative partial derivative of f with respect to x over partial derivative of f with respect to y, which you can write as negative f sub x over f sub y. This result is also known as implicit function theorem. So now we discussed this for only two variables, or y as a function of x. Now we are going to consider um, z as a function of two variables, x and y. Z is given implicitly as a function z equal to f of xy. When it is implicit, that means all x, y, z are on the same side. By an equation f of xyz equal to 0. This means that f of x comma y, because z is a function of xy, we can replace that z by f of xy equal to 0 for all x comma y in the domain of f. If uppercase f and lowercase f are differentiable, then we can use the chain rule to differentiate the equation f of xyz equal to 0 as follows. So you get dou f by dou x plus dou f by dou z times dou z by dou x equal to 0. By that, what I mean is if you write f of xyz equal to 0, and if you take partial derivative with respect to x, then y would be 0. So dou y by dou x here would be 0. Then dou x by dou x will be equal to 1. So we get dou f by dou x, which is partial derivative of f with respect to x, plus partial derivative of f with respect to z times dou z by dou x equal to 0, which results in this result, dou z by dou x equal to negative dou f by dou x over dou f by dou z. Then dou z by dou y is negative dou f by dou y, or partial derivative of f with respect to y over partial derivative of f with respect to z with a negative sign. One way to remember is if you see z on the numerator, then z will occur in the denominator here. you see x in the denominator, you'll see x in the numerator. Okay, that's one way to remember. If z is defined, if z is defined implicitly as a function of x and y by an equation of the form f of x, y, z equal to 0, how do you find dou z by dou x and dou z by dou y? In other words, how do you find partial derivative of z with respect to x and partial derivative of z with respect to y? This is just the implicit function theorem. We are restating that if f is differentiable and partial derivative of f with respect to z is not equal to 0, then dou z by dou x, in other words, partial derivative of z with respect to x is negative partial derivative of f with respect to x divided by partial derivative of f with respect to z. Same way, partial derivative of z with respect to y would be negative partial derivative of f with respect to y over partial derivative of f with respect to z. Problem number 27 and 31 are also done in the section videos. Please refer to them. Then I'll see you for my next video on 14.6. Hope this video helps.